chapter 6, the final section of chapter 6, 6.4, in which we are going to look at some more examples of solving trigonometric equations. We've worked with different kinds of trigonometric equations up to this point, using trigonometric identities and properties of algebra to try to find solutions. And so in this final section of chapter 6, we're going to consider solutions for x in terms of y, meaning that we don't actually get a value, that we just get a formula for one variable in terms of the other. So we've done things like this in algebra, where, for example, in algebra, if I have, y equals 2x plus 7, well, one of the ways we had for finding an inverse of a function in algebra was to solve for one letter in terms of the other and reverse that. So here y is solved for in terms of x, but if I subtract 7 from both sides and divide by 2, this becomes y minus 7 over 2 equals x. So then I've solved for x in terms of y. So that's what they're referring to in this first goal, solution for x in terms of y. That's something like this, where x is solved for instead of y. And then they have solving inverse trigonometric equations, meaning what if the equation doesn't have a trig function in it, but actually begins with the inverse in it. So we don't have a long section here, just a couple of goals, only 10 slides in the whole PowerPoint package for 6.4. So let's, again, like the other sections we've just looked at, they're just going to show examples. So let's dive into that. So in their first example, we have solving an equation for a specified variable. So this is what we start with. Y equals 3 cosine 2x. And we want to solve for x instead of for y. So in this case, y has been isolated and you have an expression in x, and we just want to reverse that. We want to get the x by itself and have an expression in y. Now, the big thing to remember from what we did before here is that there's values of x that you could put into the cosine 2x that would just keep producing the same answer. Cosine 2x is a periodic function, and it has a period of pi. And so every pi, you're just going to get the same answers for y again and again. So if you solve for y in terms of x, the idea is you put in a y value and you get a specific x value. But this is not a one-to-one function. And so they have to restrict x. X is restricted to the interval 0 to pi over 2. And the reason for that, as they're trying to diagram out here, is that if you look at the function 3 cosine 2x, and you make the restriction of only going from 0 to pi over 2, as they show here, then you have a one-to-one function. And so this is kind of like the process that I tried to explain in my first video on chapter 6, where when you are making an inverse function of a function that's not one-to-one, you have to restrict the domain so that that function becomes invertible. And that's what they're doing here. So once that's been set up for us, then they take the original equation and they basically just solve for x by dividing by 3 to get the 3 to the other side, then use the inverse cosine of both sides in order to get rid of the cosine on the right side, and then finally multiply by half or divide by 2 on both sides, and then they're done. And so if you understand the use of this restriction, then it just becomes a solving equation process that we've been practicing since beginning algebra, where you just get rid of the stuff around x. So you could look at the original equation and say, here's a 3, it's multiplied, so I'm going to divide by 3. Here's the cosine of 2x, so I'm going to apply inverse cosine to both sides. And cosine, then we have x multiplied by 2, so I'll divide by 2 or multiply by half. And so that just predicts the next 3 steps, and then you've got x isolated instead of y. Now, they point out in the line below what they set up in the first place with the restricted domain. It says, because the original expression had the right side with a function that had a period of pi, the restriction ensures this function is 1-to-1, as we can see from the picture. After just restricting the graph to the blue part in the diagram, you then have a graph that passes the horizontal line test. And therefore, the resulting equation, after you've reversed the relationship and solved for x, has a 1-to-1 relationship with the original one. If they hadn't done that, then it wouldn't be a complete reversal of the original equation, because you would, it's like saying the square root of x is a perfect inverse of x squared. It's not. Only if you reverse, if you isolate the domain of x squared to not include negatives. Same thing's going on here. Anyway, so that theory is probably a little harder to understand, but this process is initially where you want to focus. So students should just initially just remind themselves now that they can solve for one variable in terms of another, like they did in algebra, even if there's a trig function in there, with the use of the inverse of the trig function. The secondary issue is this more complicated issue about the proper restriction of the domain and things like that. All right, so then how do they advance with this, since the first one was sort of just algebraic in nature? So then it says, well, let's say we have solving 2 arcsine x equals pi. So what are they doing here? Well, that was their second goal of solving an equation with an inverse trig function in it. But in this case, again, it's like if you use a square root to get rid of a square, you can also use a square to get rid of a square root. The whole idea about inverse functions is that either one undoes the other. So if we look at this original equation where we want to isolate x, well, you can say, well, what's around the x? What's in the way? It's multiplied by 2 on the outside, so we divide by 2 to get rid of that. Then it's inside of an arcsine, so we take the sine of both sides to get rid of that. And that's it. And then they double check that the solution really works. If they plug the x value back into the equation, it produces a true statement, and that's the solution. So these first couple of examples, happily, are pretty simple. The procedure is very direct and straightforward to try to isolate the variable. And the big difference to try to get used to in these examples is that we're just getting rid of a trig function on one side of an equation, just like we would get rid of if the function had, if we had a multiplication or division by a number or something like that. You just do the same thing to both sides and undo everything that was done to the variable. In this case, undo what was done to x. All right, so as we begin to progress and say, well, how could this get more complicated, or what are we going to kind of look at? Let's look at this next example 3 here. So we have cosine inverse of x is equal to sine inverse of 1/2. So in this case, like with other trig functions, it becomes more complicated when the equation has more than one trig function in it, because then we can't just use that one isolated and deal with it appropriately. So if I have an inverse cosine and an inverse sine, well, if I could try to get rid of the inverse cosine by taking cosine of both sides, but the inverse sine would still be there, and vice versa. I could take sine of both sides, getting rid of the inverse sine, but the inverse cosine would still be there. So what do we do? Well, they're going to use this, so organizationally it looks kind of funny here. So I'm going to organizationally show it a little bit different than what I'm seeing them do here. They're saying let sine inverse of 1/2 equal u, then sine of u equals 1/2, and u is in quadrant 1. So why are they doing all of that? What is their process here? Well, what I'm going to point out is that what they did here is they applied the cosine to both sides to get rid of the cosine inverse. So let's focus on how they did that, and then we can look at this substitution stuff that they're doing and try to figure out why they did that or what's going on. So the main thing to point out here, just to keep it simple in terms of strategy, is that if you have the equation that they started with, you want to solve for x. So even though there's a sine inverse of 1/2 over there, that's a constant. That's just an angle. And so they're trying to sort of show that if you took sine inverse of 1/2, you'd get an angle in the first quadrant, and we even know what that angle is. And so bringing in this u variable, I think, looks a little confusing here. So let's focus on the fact that, let's say we had two colors here. Let's say we had this by itself, sine inverse of 1/2. Well, we know what the sine inverse function does. It gives us a number, an angle between negative pi over 2 and pi over 2 that would produce the 1/2 value. So you're basically saying that's what they're trying to use this u for, and saying u is in quadrant 1. But we know the angle of sine that would produce 1/2 in the first quadrant, and that's pi over 6. And so this is equal to pi over 6. So we could actually begin this equation by saying, well, I know the right side is pi over 6, and then I'm just going to take cosine of both sides and see what I get. So I think if we view it that way, it ends up seeming a lot simpler than all this work that they're doing here. So if I take this equation and say this now means that cosine inverse of x is equal to the angle of sine inverse of pi over 2, well, that's pi over 6. And so then we can say, all right, well, now I'm just going to take the cosine of both sides to solve for x. Cosine cancels with the cosine inverse. And then we get that x is equal to the cosine of pi over 6. And cosine of pi over 6 is square root of 3 over 2. All right, so let's, with me having presented my suggested simpler approach, let's try to follow through with what they're doing and see if we can make sense of it. All right, so they're saying let sine inverse of 1/2 equal u, and we know that's an angle. We know it's in quadrant 1. We actually should know that it's pi over 6 pretty quickly here. But if we did that, then if we took the cosine inverse of both sides, which they did in this step here, then we would get that cosine of whatever that angle was is equal to x, which is exactly what I had right there, except I already put what that angle is, which is pi over 6. So moving forward, when they had cosine u equals x, they say, all right, well, let's try to figure out what cosine u would be. And they're using this sort of triangle diagram to figure that out, which is a way to do this if it wasn't a friendly angle. So let's keep this in mind. So let's say you know that you get from the original part that sine of the angle was 1/2. So let's say this was theta. So they're saying we know sine inverse is 1/2 of whatever this angle is. And so if I put u or theta into a triangle, because sine of u or theta is equal to 1/2, we know that opposite over hypotenuse is 1 over 2. So opposite of the angle, we put the 1, and the hypotenuse of the angle, we put the 2. And if you plug in that 1 and that 2 that come from the fact that sine of the angle equals 1/2, you can get that the adjacent side is square root of 3. And then cosine is adjacent over hypotenuse, which would give you square root of 3 over 2. Now, the logical process they're trying to demonstrate here is really not necessary for this problem because we know sine inverse of 1/2 without having to do that. But if it was something that you didn't know, like let's say it was sine inverse of 7/3 or something like that, where we didn't know the angle, then this process makes sense. And we already did an example of that kind of problem actually in the last video I shot on 6.2. Or maybe it was 6.1 actually. I think part 3 of the 6.1. In any event, so that's what they're trying to get at here. They're not really sort of making this problem seem as easy as it could be, but they're trying to set us up for if it were more complicated than this. So let me see if I could just demonstrate that and then show you how it would look in the way that I'm doing it here. All right, so as an alternate example, so here's another example to try to show what this process is getting at. Say we wanted to solve that cosine inverse of x equaled sine inverse of, like I said, 3/7, something like that. So 3/7 is not a number where we know what the inverse sine of that would be. That's not something we're familiar with. So again, I would say, well, let's just start by getting x by itself. So I want to solve for x. It's got a cosine on it. So I would take the cosine inverse of both sides. I'm sorry, I would take the cosine of both sides, not cosine inverse. There we go. The cosine cancels the cosine inverse. And then we get that x is equal to this ugly expression, the cosine of sine inverse of 3/7. Now they used a u. I still like to use a theta because that reminds us as we're doing it that this is an angle. So then I would say to myself that, all right, this sine inverse of 3/7 here is an angle theta. And what I know about that angle theta is that when you take the sine of that theta, you get 3/7. So I would put the theta in a triangle as they did here. And then I would make the opposite over hypotenuse a 3/7. So I would put the 3 here, and then I would put the 7 here. And so then I would say, okay, well, theta is sitting in this triangle, and I know that the opposite is 3 and the hypotenuse is 7. So then by the Pythagorean theorem, I would have the square root of 7 squared minus 3 squared down there, which is 49 minus 9. So this is the square root of 40. Or I can factor out the 4 and say this is 2 times the square root of 10. Because that's the square root of 4 times the square root of 10, and the square root of 4 is 2. So the bottom side is 2 times the square root of 10. So now I have theta in this triangle where I know all 3 sides, and I'm taking cosine of that theta to get x. So cosine of that theta would be adjacent over hypotenuse. That would be 2 times the square root of 10 is the adjacent to theta, and the hypotenuse is still 7, and there's my answer. So you can bring in this sort of u substitution, or I would recommend instead of theta, just so that you keep thinking about it as an angle. But either way, that's the process they're trying to get at here. And here's another example to illustrate that. But if you're working with something like sine inverse of 1/2, and you happen to know that that's pi over 6, or that that's something you could look up on the table instead of having to do the drawing and everything, that's a little bit easier. And then if I do that, I don't need to make the drawing or make the u substitution or anything, as I illustrated on how I showed how to do example 3. In either event, as long as you could get to the right answer on a regular basis, that's great. But sometimes things are made a little bit more complicated than they need to be. And I'm always going to hope that we can develop an understanding and a comfort that allows us to not overcomplicate things, just for the benefit of students. So hopefully that helps. This was a situation where we had inverse trigonometric functions. Let's see what we have after that. So now we have something where we have a difference of inverse trigonometric functions, a difference of inverse trigonometric functions. So, and in particular, like last time, one is inverse sine and the other is inverse cosine, so they're not even the same one. Well, again, to solve for x, we're not going to be able to combine these together unless we happen to have some theorem about inverse trig functions with a difference, which we don't. So instead, we have to say, all right, in order to chip away at this, I can at least get rid of one of these inverse trig functions and then see if I can deal with the other. And so they say isolate one inverse function on one side of the equation. So they add arc cosine of x to both sides, which they did in this first step, just pointing out. And so then once you have one of those inverse trig functions isolated, you can at least get rid of that one. And so then they took the sine of both sides, which I'll just sort of fill that in, I guess. They took the sine of both sides because the sine and the arcsine cancel out, and then they get at least x isolated. Now, notice you're not done here, because to solve an equation and with a single variable in it, you need to find values that make it true. And so we've isolated x, but we have a formula, and our formula still has x in it. So the idea, hopefully, is that after doing that, we can somehow work with the right side and figure out how to combine the x's together. So what they're doing now is they're bringing in their u again, and I'm going to still say that I've had much more success with students if instead of u, we use a theta. But they're basically saying, remember that the inverse cosine of x is an angle, theta. And sitting next to it, we have another angle, pi over 6. So what we really have is you have sine of one angle like theta plus another angle, gamma or alpha or some other thing that you would use for an angle. So you have sine of a sum of angles. And they're also saying that when you take the inverse of inverse cosine of something, the angle you get has to be between 0 and pi, just by the definition of our inverse cosine function. So we have a theta in there, and we know it's between 0 and pi. So how do we deal with that? So they're putting that in. I'm going to just keep following with my theta. I think it's helpful. So I have sine of a sum of a couple angles, and now we can break that up because we have the sum of angles identities for the trig functions. So they're going to use the sine sum identity. And so then if you have sine of a plus b, or theta plus pi over 6, or u plus pi over 6, then you can get sine of the unknown angle here times cosine pi over 6, and cosine of the unknown angle times sine of pi over 6. And the value here is that we know sine and cosine of pi over 6. So we can actually get those values to try to simplify things a little bit. Now it says from equation 1, which was the one up here, the original one where we had arcsine and arccosine, and by the definition of the arcsine function. So now they're trying to see what their restrictions are about these angles. So here's where things get a little complicated. Let's say we skip over this for a second, and let's try to see what the purpose of all this is. Like, if they just do this out of the blue, it's really hard to see why any of this is helpful in any way. Eventually, we're going to have to figure out what kind of things we have, because what kind of restrictions we have on these angles, because that's the only way we can solve for x. So let's see, what are they going to do? They're going to go back to this triangle thing and see what we can do in terms of the triangle. So how would that work? We have a theta, and what we know about theta from above is that this theta value is arc cosine of x. This u, or this theta value, is arc cosine of x. So if I put that in a triangle, I put in theta, and I know that cosine of theta equals x, because theta was arc cosine of x. That means that in that triangle, the right triangle, we know that adjacent over hypotenuse is x. We know that this is equal to the adjacent over the hypotenuse. So to think of that as that fraction, if we just have an x, we're going to put that over a 1 and say, therefore, the adjacent was x and the hypotenuse was 1. So in my triangle, for the adjacent, I put an x. For my hypotenuse, I put a 1. And then I know that the opposite side then is 1 squared minus x squared under a square root by the Pythagorean theorem. Now, then if I know that, I could say, well, now I see that cosine of that angle is adjacent over hypotenuse, which is x over 1. But I also now can take sine of that angle and get an expression in x. So if I take sine of that angle, sine of theta now is equal to opposite over hypotenuse. So that would be the square root of 1 minus x squared, because that's the opposite of theta over the hypotenuse of 1, or square root of 1 minus x. And so therefore, we have an x expression we can use for sine of that angle, which is this one. And we have an x expression we can use for cosine of that angle, because we know that's just equal to x. cosine of theta is equal to x from over here. And sine of theta is equal to square root of 1 minus x squared. And so now I can replace each of those with that expression in x, and I can evaluate cosine of pi over 6 and sine of pi over 6. Cosine of pi over 6 is square root of 3 over 2. If it's evaluated in exact value, and sine of pi over 6 is 1/2. And so now all of the trig functions will go away if I make these evaluations. So they're trying to come up with that here at the triangle. So they get sine of the angle is equal to 1 minus x squared using the triangle as I showed you a second ago. And so they plug in all 4 of those parts that I just described, and this entire equation reduces to this. And this is pretty huge here. So there's the big, huge step to think about. And then after that, they spend some work trying to solve that for x. But let's take a look at what they did here. So they had sine of u, cosine of pi over 6, cosine of u, sine of pi over 6. And each one of those 4 things, they then replaced with those 4 parts that I was describing above. So after having done all of that, well, then they can take this final equation and solve it algebraically. Now all the trig functions are gone. It's just in terms of x. And so how do they solve this for x? Well, they have some like terms. They first had a couple of fractions, so they cleared fractions. Let's just show what their motivation is here so we can understand what their steps are. Oh, that's terrible writing. There we go. They clear fractions by multiplying by 2. So if you multiply both sides by 2, these denominators go away. Of course, you have to multiply on both sides. So then they're left with 2x equals root 3, because square root of 3 over 2 just becomes root 3. And the 1/2 goes away, leaving x. Now that the fractions are gone, they have some like terms with x's. So they subtract x on both sides to combine those together. It's getting better and better as they go down here. And so then we have x equals a square root of 3 times another square root. Well, both of those things have square roots, and we want to get at the x inside, so they square both sides. They square both sides because that'll get rid of the square roots. Keep in mind, because they square both sides, you must check solutions. As we were talking about earlier, whenever you square both sides of an equation to get solutions of that equation, you may get invalid solutions along with any valid solutions that might exist. So all solutions must be checked. We saw an earlier problem in an earlier video where we initially had 6 solutions to an equation after we squared both sides, and only 3 of them worked. So you just always have to check solutions if you square both sides when solving an equation. But once they've done that, the roots go away, the left side becomes x squared, then they can distribute, combine like terms, and they end up with just 2 possible solutions initially. At this point, if you square rooted both sides, you would say, oh, this is plus or minus the square root of 3 over 2. If I literally just square root both sides, you'd need to have a plus or minus. And then it says choose the positive root because you know x has to be greater than 0. That goes all the way back to one of the things they talked about in the beginning. Why do we know x has to be greater than 0? Well, because where was it here? X has to be greater than 0. Somewhere I thought we pointed that out specifically. I guess it's because the simplest place to see it, I thought it was done early on, but I guess I was wrong about that. The simplest place to see it was here. So I apologize for thinking it was earlier, but it was not. Right at this point alone, we have a radical, which is positive, times a radical, which is positive, which equals x. So they didn't point it out here, so maybe I should have done that. The right side has to be positive here. So that means that therefore x has to be positive since x is equal to that. So we would only take the positive root here. And so then since we're only taking the positive root, we just get one possible solution. Now it says check the solution in the original equation. That sounds like a good thing just to see that it works, but you must do that because we squared both sides earlier in the process. So what happens? Either this one possible answer we have works in the original equation, and then it is a solution and the only one we could get. So it's a unique solution, or it doesn't seem to work. And if the only one that could work doesn't, that means the original equation has no solution. And that's always possible, especially with real numbers that you're looking for. So just for example, keep in mind, if I have x squared equals -1, that has no solution. That has no solution because I can't square a number and get a -1 in the real numbers. So it's quite possible you can have an equation with no solutions. And so if we had checked this answer and it didn't work, we would say there's no solution to the equation. But as we see here, when they plug in square root of 3/2 to both sides, you actually do get a true statement, and we do get a valid solution, and that's the only one there is. And so that's the solution. All right. So that's it. So that's a pretty complicated one. And it was a little bit involved. Both the algebra was involved, as well as we had a couple of inverse trig functions. So I would suggest for students, don't worry about the hardest examples when you're trying to get started in each of these sections. Work with the easier examples first until you get a little bit more comfort with the process. So for our slideshow here, the first couple examples were quite a bit easier and more straightforward, just so that we could get used to, for example, if I have a cosine, I can inverse cosine both sides. If I have an inverse sine, I can sine both sides, things like that, just to get used to that as a solving process. And then as they get a little bit more involved, you can look at more complicated examples, or of course, bring those nastier problems that you're confused by to tutors or to class where we can discuss it. And I think that's where you'll make the progress you need to make. So hopefully this helps. Keep up the hard work, and let's move on to chapter 7 after we're done with chapter 6.